Hello there, Mr. Sutton here, bringing you the AB Calculus 6-8 Extra Practice Number 1 solutions on motion-free response problems. On this problem, we have a particle q moving along the x-axis with a velocity given by this function over here and the acceleration given by this other function. And we're told that the particle's at position 2, x equals 2 at time 0. So first part of this problem, on the interval 0 to 5, we want to know when is the velocity of our particle increasing. Well, if I'm talking about when velocity is increasing, I'm talking about v prime. And v prime we know is really the same as the acceleration. So I just need to figure out then when my acceleration is positive. So I'm going to set this equal to 0 and then go ahead and graph this out on my graphing calculator. So I've entered two things in my y equals on my calculator. The first in y1 was this velocity formula, and the second, since they kind of gave it to me for free, was this acceleration formula in y2. But now out of both of these, I just want to graph y2 for this problem. So I'm going to go up here and deselect my velocity function. So I'm just graphing acceleration. Where am I graphing acceleration? Well, they're asking about on the interval 0 to 5. So I am going to go to Window, and I'm just going to put in from 0 to 5 for my x min and my x max. And now let me do zoom 0, zoom fit, and that'll give me the perfect window on my acceleration function. So there it is, my acceleration function. And we have a crossing over here, it looks like, at 0. We also have this crossing over here. So let me do second trace and then 0. And let's see here, let me just arrow over here, enter a little bit to the left, press enter again a little bit to the right, down there, and enter one more time just because. And that gives me about 3.963 if I round that off. So that's the time at which the acceleration is exactly 0. Now looking at this graph here, which I'm looking at, this is just a picture of what I have on my grapher, I notice that my acceleration is positive above the x-axis between 0 and also 3.963. And if you weren't sure that this was crossing at 0, let's go back to the grapher, and we can do second trace 0. And now let me just scroll back here. And let's see here, all the way back past 0, because it is kind of weird, like, where does this actually cross? So going back here, arrow back a little bit. It's taking some time to think about this. All right, there we go. So left bound a little bit to the left of the origin, right bound a little bit to the right, enter one more time, and we see that indeed, come on, you can do it, there we go. We have a 0 at this crazy weird number, which is just the calculator's way of saying 0, because that's just about as close to 0 as you can get. We are going from 0 to 3.963. So that's where the velocity prime is positive, so therefore that's where our velocity is increasing on that interval. For this part of the problem, I want the position of particle q at time 3. I have the position at time 0. They told us it was 2. So I can use my fundamental theorem of calculus with this starting position and the integral of my velocity here to figure out pretty much any time that I want what the position is. All right, so let's do, let's see, x of 3 is going to equal x of 0, which is 2, plus the integral from 0 to 3 of my velocity. And I need to do this on the calculator. So I've got 2 plus math 9, and then we're going from 0 to 3. And my velocity, I actually stored that as y1 in my y equals. So let me just do alpha trace y1, and then dx. And let's see what this comes out to, about negative 1.490. So that is our new position. For this part of the problem, we have a second particle, r, moving along our x-axis, so that its position is given by some differentiable function, x sub r of t. And then they give us two values of x sub r at 1 and 3. They want us to explain why there has to be a time between times 1 and 3 where our velocity of particle r is 2. So if we're given the initial function, the original function, and we're being asked to guarantee values of its derivative, that's usually a mean value theorem kind of situation. So let's find the average rate of change from 1 to 3 of this function. So that's going to be x sub 3 minus x sub 1 over 3 minus 1. This is our average velocity of r, average rate of change of particle r. So that's going to be 8 minus 4 over 3 minus 1. 4 over 2 gives us a value of 2. So we've got the same a rock as the I rock that we're looking for. Now we just have to kind of bring this home by justifying it with the mean value theorem. So the other precondition, other than a rock matching the I rock you want, is you need a differentiable function. And we're told that this function is differentiable. So since x sub r of t is differentiable everywhere, and our average rate of change on the interval that we're looking at is 2, our mean value theorem, MVT, guarantees a time on this interval where the I rock, namely the velocity of r, is also going to be 2. For this problem, at time 3, they said the velocity of a particle r is negative 2. They want to know if particles q and r are moving toward or away from each other at time 3 and explain our reasoning. All right, so we know some information about particle r. We've got its velocity at time 3, which is negative 2. And they also told us in part C that it had a position of 8 at time 3. But how about the q particle? We found the position of q at time 3 based in part B, but how about the velocity at time 3? So that's the only piece of information we're missing is velocity of q at time 3. So plugging that in my calculator now, let's see, that's going to be y1, so alpha trace y1 of 3, and that's coming out to 1.682. So that's what we're doing. We're moving to the right at time 3 for particle q, and from part B, remember we had negative 1.490 for the actual position. So we are starting to the left of the y-axis and moving to the right. Now for particle r, we said that we had a velocity of negative 2. They told us that in part D. In part C, they told us the position at time 3 was 8. So here we are starting to the right of the y-axis and moving to the left. So since q is negative and moving right, and r starts positive and is moving left, our particles must be moving toward each other because they're both moving toward the y-axis. On this problem, we have Karen riding her bicycle on a straight road from home to school. Her velocity is given by this graph here, and for part A, we want to figure out her acceleration at time 7.5. So we know that acceleration in general is the derivative of velocity, so we can say a of 7.5 is really v prime of 7.5, and we can look up v prime on the graph here. It's going to be the slope of this velocity graph at time 7.5. So that's right about here, and since this is a straight line, we just need to figure out the slope of this line. So that's going to be, for the y values, we've got 0.2 minus 0.3. For the x values, we have 8 minus 7. And you could do this on a calculator or not. This is negative 0.1 on top, 1 on the bottom, so negative 0.1 overall. And since our units on this one is going to be, let's see here, we have minutes for the time. We have velocity is miles per minute, so acceleration is going to be miles per minute squared. So negative 0.1 miles per minute squared. For this next part, we want to use correct units to explain the meaning of the integral from 0 to 12 of absolute value of velocity in terms of Karen's trip. So whenever you see absolute value of velocity inside an integral, you're essentially just calculating the total distance. So this is going to be the total distance that Karen travels. And this is going to be in units of, let's see here, miles. And we also have to involve the time element. So this is how far she travels in total distance from 0 to 12 minutes. Next, they want us to actually find the value of that. So to do that, we're going to need to use some geometry. We're essentially going from 0 to 12 and just adding up all the areas. And because this is total distance, all the area has to count as positive. So we have first this triangle here. This is 1/2 times a base of 2 times a height of 0.2. And now we've got this other triangle, which is actually going to be the exact same dimensions, so base of 2, height of 0.2. Next, let's see, this doesn't count. We've just got a horizontal line on the x-axis. But next we have, let's see, either a trapezoid or a triangle, depending on how we play this. I think I decided to go with a trapezoid here. So we have a base of 1 plus a base of 2 all over 2 times a height of 0.3. So this is a trapezoid that's essentially on its side here. Next, well, actually, it's normal trapezoid. All right, this next one though is going to be on its side. This is a trapezoid from 7 to 8. So let's see here. I've got a base of 0.3 plus a base of 0.2. Now my bases are lateral here, and we've got that divided by 2 times a height of 1. And finally, this last thing is one big trapezoid, base of 3 plus a base of 4 over 2 times a height of 0.2. You could stick units on the end of this, they're miles, and be done with it, or you can add it all up on the calculator. All right, so this would be firmly in the category of kids, don't try this at home. A whole bunch of things being added together here. Again, totally unnecessary. Fancy fraction form helps a little bit on this. All that should come out to about 1.8. And again, that's going to be miles. On this next part of the problem, shortly after leaving home, Karen realizes that she left her calculus homework at home. Oh no, Karen! And she returns to get it. Good. At what time does she turn around to go back home? Give a reason for your answer. Well, she's moving on a straight road to school, and while she is moving towards school, she has a positive velocity. But if she starts going backwards, she's going to have a negative velocity. So we can say that Karen's going backwards on the road back home when her velocity is negative. And where does velocity turn negative on this graph? Well, that only happens in one spot. We're turning from positive to negative at time 2. So that is the time when Karen is going back home and turning around. For the next part of this problem, we have a new character, Larry, riding his bike along a straight road from home to school in 12 minutes with a velocity modeled not by a fancy graph, but by this even fancier function right here, W of t. So we want to know who lives closer to school, Karen or Larry, and show the work that leads to the answer. All right, well, let's work with Karen first because we've been working with her this whole time, so we should get a sense of closure here. When we're calculating how far Karen has actually ridden by the time she gets to school, or at least how close she is to school, we're no longer talking about total distance. We found her total distance earlier in part B by adding up all the positive areas in this graph. But we now want to have Karen's displacement. That means that these two triangles here, for when she rode a little ways, figured out she left her calculus homework at home, rode all the way back, these two triangles don't count because she went back home. All that counts for Karen is when she actually started riding towards school. Okay, so we need to find this area here. Now that's kind of annoying because you've got, let's see, 1, 2, 3 trapezoids to find again, all over again. Another way you could do this is you could take her total distance and just subtract the area of these two triangles. So her total distance, remember, was 1.8. So the integral from 0 to 12 of just velocity with no absolute value is going to be that total distance minus these two triangles, each of which was 1/2 times a base of 2 times a height of 0.2. So this situation right here. Well, the 2 and the 1/2 cancel, so this is just 2 times 0.2 or 0.4. 1.8 minus 0.4, and you could have used a calculator, but I'm not going to. That was 1.4 miles that Karen actually rode to get from home to school when all was said and done. Now, how about Larry? Well, for Larry, we're going to need to use the calculator. We're going to set up an integral. Larry's displacement is going to be given by the integral from 0 to 12 of Wt dt. And now for the calculator. To make my life a little bit easier, I'm just going to put Larry's function as y1 so it's easier to manipulate and move around. And now I'll do math 9 from 0 to 12, we said, of alpha trace y1. So this is Larry's velocity here, and dx, and that all comes out to 1.6. So between the two of them, it appears that Karen lives closer to school. For this problem, I have a particle x moving on the x-axis, and its position is given by this function here as a function of time greater than 0, or equal to 0. For the first part of the problem, we want to know if we're moving left or right at time 1. Well, if I want to know the direction, I need the derivative of x. That's going to tell me whether I'm changing to the left or changing to the right in my position. So x prime of t, which you could also call the velocity, is 15t squared minus 18t. And now we just have to plug 1 into that. Plugging in 1, this is going to come out to negative 3, which most importantly is a negative number. So that means that since we're going along the x-axis, we're moving in the negative direction, which is to say we are moving to the left at time 1. For this part of the problem, we want to know at what time greater than or equal to 0 is our particle farthest to the left, and justify the answer. So for this we need x prime again, which we already defined in part A. So that again was 15t squared minus 18t. We're going to say here, we're going to set that equal to 0 and solve for critical values. We want to figure out when this thing is actually turning around. That'll help us decide when we are as far left as we can go. So to solve this, because this was a no calculator question, I need to factor. I can take out a 3t, leaving me with 5t minus 6 inside. So then we get critical values of 0 and 6/5. Let's go ahead and put those on a number line now to check out the directions. So we're going to do some sign analysis for x prime. Here was 0, which also happens to be an endpoint, because time must be greater than or equal to 0 to be considered here. And then we have our critical value, our other one, at 6/5. All right, plug in something between 0 and 6/5, such as 1, seems like a good candidate. That's going to be a positive times a negative, which comes out negative. And if I plug in something bigger than 6/5, like 2, now we've got a positive times a positive, comes out positive. All right, we don't have a closed interval here, so we can't just test the endpoints and the critical value. What we're going to do instead is look at the direction this thing is going and just kind of reason it out by the directions that we're heading in here. So we notice that from 0 to 6/5, we are going to the left. We are heading in a negative direction. X prime is less than 0. And then I also noticed that if t rather is greater than 6/5, well, now our x prime of t is positive. So this means we're from time 0 to time 6/5, we're going left. And then we stop going left right here, and we start moving to the right. So you can't get any further left than you are at this time 6/5, because you've been moving left this whole time. That means that any time before 6/5, you're not as far left as you can go, because here you've gone further left. But then after we get to 6/5, we just start moving to the right. We never move left again. So this is as good as it gets. We can conclude based off of this that x is farthest to the left if time equals 6/5. For this next problem, we have a second particle mixing things up, particle y, going along the positive y-axis, and its position is given by this y of t function right here. So at any time greater than or equal to 0, the origin and the positions of particles x and y are the vertices of a triangle in the first quadrant. So just to draw out the situation here, here's my little drawing up here. Here's the x-axis with half an arrow there, I guess, my y-axis, and here's this triangle. So we have the origin, we have x of t over here, we have y of t over there. And this is giving us a triangle that has a certain area. We want to find the rate of change of the area of this triangle at time 1, and then show our work. So let's start by writing a formula for the area of this triangle. In general, area of a triangle is 1/2 base times height. The base in this case is just x of t. It's this horizontal distance. The height is y of t, this vertical distance. So we can write that the area at time t equals 1/2 x of t times y of t. And we need to essentially take the derivative of all of this stuff and then plug in 1 for t to get this a of t value. All right, so in general, since I've got two functions being multiplied, I can use the product rule. Alternatively, since you actually know what these functions are and they are both polynomials, you could just multiply x of t and y of t together, simplify it, and then use your power rule. But I'm going to go product rule in this one. So that's u prime v plus uv prime. I'm not sure if this is faster or slower, but we're going to do it. So over here, my box and ribbon, I've got the x of t here, 1/2 times x of t, so that's 1/2 times all of this stuff. And then y of t is just this stuff over here, 7t plus 3. Now they're derivatives. Normally inside here I'd have 15t squared, so that's 15 over 2t squared, minus this 2 and the 1/2 cancel, so that's just minus 9t. 7 gets differentiated away. Over here, I've got, this is y prime now, I've just got 7. And all I have to really do is plug 1 in. So I'm just going to plug it all in inside my box here. So if t equals 1, then we can write the following for each of these values. So up here, let's see, I've got, this is 5 times 1 is 5, minus 9 is negative 4, plus 7 is going to be 3. So this is 3 over 2 for that value. Over here, I've got 7 plus 3. I love plugging in 1. So 7 plus 3 is just 10. Down here, this is 15 halves minus 9. 9 is really 18 halves, so this is negative 3 halves. And down here, 7 is playing itself in this motion picture. Now I just do my ribbon. So I've got negative 3 halves times 10 plus 3 halves times 7. And it didn't look like they give me any units here. So I could actually just leave it like this and call it a day and be done. Or if I feel like risking losing points, I can go ahead and simplify this. So let's see here. I'm just going to keep everything in terms of halves because that's what it looks like I have in both of these terms. So this is negative 30 over 2 plus 21 over 2. That's going to come out to negative 9 over 2. So that's as simplified as it's going to get.